So let's try and finish what we set out to do for the day. So the next theorem, theorem 3, is a sort of converse of the theorem above. In what sense? So it says, well, hey, okay. So So it says, suppose I have some V, suppose V solves V of x naught is equal to sup f of x naught x1 plus beta V of x1, overall feasible x1, yeah, feasible from x naught. So suppose V is some function that's a solution to this functional equation, right? So then theorem 3 gives conditions under which, so conditions under which V is actually V star, that is the value function to the sequences problem. And these are again very mild conditions. So the theorem says, suppose x gamma f beta satisfy assumptions 1 and 2. Suppose V is a solution to the functional equation, and V also satisfies this property 8, which is that for all starting states x naught and all feasible plans x tilde starting at x naught, these feasible plans satisfy that the limit of beta to the n V of xn goes to 0 as n tends to infinity. If this additional condition is satisfied as well, then V, the solution to the functional equation, is actually just V star, the value function for the for the sequences problem. So what does this mean? Look, so as n grows large, beta to the n grows small. In fact, it goes to 0, right? V of xn is the value, if you interpret it as the value to the decision maker of, if you interpret it as some discounted present value to the decision maker, when the decision maker is sitting at time t equals n, yeah, and has inherited the state xn, yeah, inherited xn, sitting at, so dm is sitting here, yeah. So it should not be that, so it should be that when the decision maker sits actually at time t equals 0 and thinks about this, the reward to the decision maker will be beta to the n V of xn, yeah. This should go to 0 as n tends to infinity. So in some sense, this V of xn should not grow faster than the beta to the n is declining. Right? So if V of xn were to grow faster than beta to the n declines, then this thing will not go to 0. Okay? So if this condition is satisfied, so it looks like something of a transversality kind of condition. If this condition is satisfied, then the function V that solves Bellman's equation will be V star, the value function to the sequences problem. So we'll do the proof for the case where V of x naught is a real number, where V of x naught is finite, right? The case where V of x naught is plus infinity is kind of quite tedious. So we don't do it here. It would be good if you read and follow the proof at least once from Stokey, Lucas, and Prescott. It's not something to be memorized. And V of x naught is equal to negative infinity is a case that's fairly straightforward again. So we focus on the case where V of x naught is finite, okay? So what do we have? We have that V solves Bellman's equation as above. V of x naught is finite. What do we want to establish? We want to establish that V of x naught is equal to V star of x naught, where V star of x naught, remember, is the soup over, all these infinite series that look like that. Yeah, so this is notation for that, or both are sort of interpreted as limits of partial sums. So soup over all the u of x tildes that you can get over all feasible plans x tilde that start at x naught, right? So we want to show that V of x naught is this. So how do we show it? We show first and foremost that V of x naught must be greater than or equal to U of x tilde for all these feasible plans starting at x naught. And we also show that if we take any epsilon greater than 0, even a very small epsilon, a vanishingly small epsilon, we'll find an x tilde such that U of x tilde is so close to V of x naught that when we add epsilon to it, it's greater than or equal to V of x naught. Okay, so that will establish that V of x naught has all the requirements to be a supremum over the set of all U of x tildes. Right. So first, we want to show that V of x naught is greater than or equal to all possible U of x tildes, where the x tildes are feasible plans starting at x naught. Right. Okay. So we have to establish these greater than or equal to 0 properties. So what we do is we take the property that V of x naught, that V is a solution to the functional equation. That means that V of x naught is greater than or equal to f of x naught x1 plus beta V of x1 for all x1 that are feasible at x naught, right? And we keep unpacking the V. Okay, so we have a V of x1 here, but because V solves the functional equation, V of x1 is greater than or equal to f of x1 x2 plus beta V of x2. And so if we replace the V of x1 with the right hand side here, we get a greater than or equal to sign here. So that's greater than or equal to f of x naught x1 plus this beta times f of x1 x2 plus this beta times beta V of x2, which is this. Just keep unpacking it for over n steps. Okay, so if we unpack it over n steps, this part carries over for n steps, and that will just give us something that looks like a summation of the f of xt, f of xt plus 1 terms, t starting at 0. So we start with beta to the 0, 1 times f of x naught x1. So that's this term. Then we get beta to the 1 times f of x1, x2, and so forth. Do it for n steps. That's our partial sum, which we wrote like un x tilde, the partial sum over discounted present value over n periods, or n plus 1 periods, 0 to n, across this feasible plan x tilde, right? And this, after n steps, becomes beta to the n v of xn plus 1. Okay, so now if we take limits, the right hand side goes to, this goes to that just by definition, because this is the limit of the partial sums, and by the assumption in the theorem, this goes to 0, right? And so that must mean that v of x naught is greater than or equal to u of x tilde plus 0. And in this argument, we've at each step, at each step, we have a greater than or equal to for any feasible next step state. So for any feasible x1 in the next stage, for any feasible x2 at the next stage. And so this argument holds for any feasible plan. All right. So that's the first requirement for v to be equal to v star in the sequences problem, right? The second requirement is that to show that the v of x naught is an adherent point. Okay, so given epsilon greater than 0, we need to show that there exists x tilde such that u of x tilde is very, 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 very close to v of x naught, so that when you add epsilon to it, that's greater than or equal to v of x naught. Okay, so you start with any epsilon greater than 0, and we'll do the following. So choose a sequence of positive real numbers delta t going from 1 to infinity, such that when I multiply delta t with beta t minus 1 and I add all of these up, it gives me something less than or equal to epsilon by 2, right? So there are many ways in which I can do this. All that it's asking me to do is to choose these delta t's to be sufficiently small that the discounted sum is less than or equal to a given epsilon by 2. If you want, you can play around and come up with an actual sequence of these delta t's. Okay, and the other thing is that so we're going to be using the fact that, for instance, that we can find some x1, for instance, such that f of x naught x1 plus beta v of x1, when we add our small delta 1 to it, that this becomes greater than or equal to v of x naught. Okay, since v of x naught, since v satisfies the functional equation, for every delta 1 greater than 0, greater than, we can find an x1 such that this term, some of these two terms are so close to v of x naught that when we add delta 1, this becomes greater than or equal to v of x naught, right? We can do this at any stage t, okay, that we can find an xt plus 1 that is feasible such that the first two terms are very close to v of xt, so that these plus delta t plus 1 are greater than or equal to v of xt. So if we start doing this at time t equals 0 and we do this for a large enough n, right, then because the beta to the n v of xn goes to 0, we should be able to find a capital N such that for all small n beyond that, this is less than epsilon by 2. Okay, so if we do that, we have this. We started with this, then we, so then, like in the last step, this is less than or equal to f of x naught x1 plus beta, and this v of x1 is less than or equal to f of x1 x2 plus beta v of x2 plus delta 2 plus delta 1 and so forth. Okay, so after n steps we have these two terms to start off with, plus other terms to get this partial sum, right? And then we have this, this beta squared v of x2 term after n steps becomes beta to the n plus 1 v of xn plus 1. And then we have a sum that looks like delta 1 plus beta delta 2 plus beta squared delta 3 blah blah blah. That's this term. Okay, now because the infinite term is less than or equal to epsilon by 2, so is this. Okay, so after n steps we have this, and now what happens when we take limits? Well, this goes to u of x tilde, where notice that we're at each step we're finding an x1, feasible x1, then feasible x2, etc., so that the resulting f plus beta v term is very close, as close as we want, is delta close to the v of xt's. Okay, fine. So then by definition the limit of these partial sums is this discounted present value from 0 to infinity, right? These go to 0, or well, so these stay at less than epsilon by 2. This stays at less than or equal to epsilon by 2. So the whole thing is less than or equal to u of x tilde plus epsilon. So we found an x tilde such that the u of x tilde is so close to v of x naught that when we add this small epsilon to it, this side becomes greater than or equal to v of x naught. So v of x naught is an adherent point of the u of x tildes, right? And you can take a look at the plus infinity, minus infinity cases. Okay. So here's an example in which it's not the case, so in which we'll find a v that satisfies the functional equation, but we'll also find a feasible plan x tilde along which limit beta to the n v of xn will not be 0 as n goes to infinity. Yeah, and it will be the case that this particular v that we find that solves the functional equation, it will not be the value function v star. Okay. So what is the example? There's a decision maker with discount factor beta strictly between 0 and 1, and the decision maker can borrow or lend any real amount at a 1 period interest rate which is 1 by beta. So it depends on the discount factor, but this is not, so if you do some macro, you'll agree that this is not something that I've pulled out of nowhere. Yeah, so 1 period interest rate is 1 by beta minus 1. Okay. So, right, so what it's saying is that if I lend 1 to you, then I'll get back 1 by beta tomorrow. Okay, which is greater than 1. And if I borrow 1, then I owe you 1 by beta tomorrow. Okay. If you've read this, it ought to be clear, right? So what is the sequences problem here? The sequences problem is you maximize summation beta to the t ct. Okay. So the u of ct is now just ct, that is the decision maker is risk neutral. And often the kind of u of ct that we have is, so often most often we have u of ct such that u double prime of ct is strictly less than 0. U prime of ct is strictly greater than 0, right? So there's some marginal utility of consumption that is positive, but it's strictly diminishing. So because it's strictly diminishing, in any period you have the urge not to just keep consuming. So because the increment on your marginal utility keeps decreasing, right? So you have some incentive to spread your consumption over time. Yeah. In this example, that incentive is missing. But having said that, we'll give some consumption paths that where the decision maker consumes over time. Okay. So now maximize this, right? So this is not written only in terms of states simply because it's a little bit easier to write it this way, but that's okay. So maximize this subject to your consumption being non-negative and being less than or equal to xt minus beta xt plus 1. So what does that mean? So this part is simply saying that, so suppose I don't want to throw away the good, right? So if I do consume, I want to consume up to my capability, right? Not less than that, because this increment up to this will give me some bang here in the utility, right? So what is this saying? So if I rewrite that, it's saying beta xt plus 1 is equal to xt minus ct, or xt plus 1 is equal to xt minus ct by beta. What is that saying? It's saying the following. Suppose my wealth was xt to start with in period t, and I consume some ct which is less than the wealth, right? So xt minus ct greater than 0 means I lend this out. I lend this amount out, and tomorrow I get back xt minus ct with interest. So I get back this amount, and that's my wealth next period, it grows. On the other hand, if xt minus ct is negative, right? Yeah, so that means, you know, my ct is exceeding my xt. How do I manage that? I manage that by borrowing this amount, the remaining amount, right? So next period I have to pay back, you know, this is debt, I'm indebted and I pay back this amount. So my debt xt plus 1 grows. Okay, but in this example I'm permitted to borrow without limit. Okay, so there is no hard borrowing constraint. I can just, so if there's no hard borrowing constraint, then for instance, you know, this is one, the following is one feasible consumption path, yeah, which is at each time ct I consume something that makes beta raised to the tct is equal to 1. So if I do that, then what I get from here is a sequence of ones to add up, you know, and that goes to infinity, right? There are many other consumption plans that go to infinity as well, but this means that when I maximize, yeah, when I take the soup, doesn't matter what I start with. I had set the starting wealth equal to 0. It doesn't matter if it's positive, if it's negative. I can always do that by borrowing. So that means that V star, irrespective of what x naught is infinity. Okay, so my value function V star of x is equal to, or let's say x naught is equal to plus infinity for all x naught that are possible starting values, right? So that's my value function. Okay, so what consumption path actually equates beta to the t ct is equal to 1? It must be that ct is equal to 1 by beta to the t, right? So consumption, since beta to the t is going to 0, consumption is exploding. Yeah, it's exploding to keep beta to the t ct equal to 1, right? Fine. Yeah, so notice that actually if you look at theorem 2 says if my sequences problem environment satisfies assumptions 1 and 2, that is that the limit of partial sums exists and there are always feasible states that I can choose, then the V star that I have will solve the functional equation. And you can see that that indeed is the case. You know, what is the functional equation here? So, you know, ct is equal to xt minus beta xt plus 1. I replace the current state with this notation x and tomorrow's state with xt plus 1. So c is equal to x minus beta y. Using that, I can write the functional equation for any function v to be v of x is equal to soup consumption x minus beta y plus beta times v of y, where the next period state y that I choose has an upper bound x by beta. Okay, so what is this saying? So please notice that I had this evolution for wealth or debt. Okay, I'm calling this a y now and this an x. So let me call that a c. So what this is saying is that the largest that my wealth tomorrow or my debt tomorrow can be, I get by setting C equal to 0. Okay. So if I don't consume anything, that's the largest my wealth can be. It can go up to X by beta. Okay. But what is the smallest that it can be? There is really no lower bound because I can borrow anything I want. So I can, if C is very, 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 very large, so X minus C is something, no matter what my wealth X this period is, this can be very, 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 very negative. Yeah. And so X minus C by beta, my next period's wealth, can be very, 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 very negative. Yeah. So this is the functional equation. So does V star is equal to infinity for every X naught. Does it satisfy this? Well, V star of X naught is equal to sup X naught minus beta X1 plus beta V star of X1. X1 belongs to very negative to X by beta. Indeed, yes. I can plug in an infinity here. This is something finite. To that, I'm adding an infinity here. Infinity is equal to infinity. Yeah. So, I hope you'll permit me to say infinity is equal to infinity because I'm using here the set of extended real numbers. Okay. So sure. So as expected, theorem 2 goes through, right? Theorem 3 will go through for a particular function V that solves the functional equation or Bellman's equation, provided that along every feasible path x tilde, limit beta to the n V of xn goes to 0 as n tends to infinity, right? So I'm not going to treat the V star there. Remember that this is this transversality kind of condition. Here, it's a sufficient condition for a particular solution V of the functional equation to be the value function V star. Okay, it's a sufficient condition. So we'll give another V that solves this functional equation and a feasible path x tilde where beta to the n V of xn does not go to 0. And in fact, we'll see that, well, it's also the case that this particular V is not V star. Does that say very much? Maybe not, because remember that this is a sufficient condition. If there is a V that satisfies this on all feasible paths, then V is equal to V star. If a particular V is such that along some feasible path it's not satisfied, we don't know whether that's equal to V star or not. Okay, but in this particular counter example, it's not, right? So what is that example? It's the following. So the function V of x is equal to x for all x, satisfies Fe. Okay, so Fe will then look like, on the left, I'll have an x, and on the right, I'll have x minus beta y plus, since V of y is equal to y, that's the function, I have this. These cancel out, so what y I choose doesn't really matter. Okay, for this particular v. It doesn't matter. I have an x is equal to x, right? So v of x equals x for every x is another solution to this functional equation, right? So with this solution, consider the following path. So suppose I start with some positive wealth, right? The following plan is feasible for me. I don't consume anything, anytime. Okay, it's a feasible plan. I lend all of this. So then next period, my wealth grows to x naught by beta. Then I lend all of this. So next period, my wealth grows to x naught by beta divided by beta. That and so forth. That's a feasible plan. Okay. But then what is beta to the n v of xn? It's beta to the n x naught by beta to the n. That's x naught. It doesn't go to 0. Okay. So here is an example of a function v that solves the functional equation, but along with this particular feasible path, this condition that it go to 0 as n tends to infinity, that fails. Okay. It's not a necessary condition, it's a sufficient condition, yet in this particular example, this v is not the, it's not the value function. The value function we know is v star of x is equal to infinity for every x. Okay. All right. So the next theorem has something to do with an optimal plan. So I need to define what an optimal plan is. So let's say a feasible plan x tilde is optimal starting at x naught if the discounted present value that I get from this plan is actually v star of x naught. It attains the supremum. Okay, so we'll use the x star notation for an optimal plan. So let x tilde star be the following: x naught, but x naught, let's just call it x star naught, doesn't matter. And then we go to x star 1, x star 2, etc., etc., choices for future states, such that from this feasible plan, the discounted present value actually is the supremum. It's the maximum possible starting at x naught. Okay. That's an optimal plan. So theorem 4 says that if x tilde star is a feasible plan that is an optimal plan from x naught, then this set of equations is satisfied. What is that? It's that we start at x naught. Okay, I can call it an x naught, I can call it an x star naught, whatever. We start here. Here, this equation is satisfied, that this is equal to f of x naught x star 1 plus beta v star x star 1. Okay, that's satisfied. Then at x star 1, the following is satisfied: v star x star 1 is equal to f of x star 1 x star 2 plus beta v star x star 2. Yeah, and so on. You know, in period t, v star x star t is equal to the right hand side here. Okay, so the theorem says, suppose my x gamma f beta satisfy assumptions 1 and 2, In that case, if x tilde star is an optimal plan, that is a plan whose discounted present value attains the supremum for the sequences problem, then V star actually satisfies these equations. So what is the significance of this? Look at this one. Yeah. So we know that if x, gamma, f, beta satisfy assumptions 1 and 2, then V star satisfies the functional equation, right? So V star will satisfy V star of x naught is equal to sup f of x naught x1 plus beta V star of x1 over all feasible x1, right? So now we are saying that, look, this is satisfied over all feasible x1. What if I pluck my x1 out of an optimal plan? So I set this equal to x1 star, x1 star. Then this will actually attain the sup. Yeah. So V star of x naught is equal to that, is equal to sup. Okay, because V star anyways satisfies Bellman's. This is Bellman's functional equation. Yeah. So what is being said is now if instead of the x1 I put in the x star 1 from the optimal plan, yeah, I'll have this equation, right? So that sounds very reasonable, right? That if I take the sequences optimal plan and I take those x star t's and I plug them into the right hand side, they will attain the supremum of the Bellman equation. Okay. What is the other significance of this? The other significance of this is that suppose I have solved the sequences problem and I found, so suppose I found an optimal plan, x star tilde. Yeah. And at t equals 0, I choose my next period state to be x star 1. Fine. So I attain this sup. All right. Then I now come to period t equals 1. Okay. So I have to choose an x2 from gamma x star 1. What do I choose? So what this is in some sense saying is that if I choose x star 2, I get f of x star 2 blah 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 plus beta v star x star 2, right? So what this is saying, equation 9 here is saying, is that this is exactly v star x star 1. It's the supremum, it's the max value that I can do. So this is saying that suppose I've solved the sequences problem and I have an optimal plan. As I go further and further down time, I will have no reason to change the plan. Okay, the optimal plan is optimal at t equals 0 in the sense that it maximizes u of x tilde, right? But it's also optimal at t equals 1. Okay, it's still doing the maximization job at t equals 1, because on the left hand side, you know, what I attain here on the left hand side is the max, the v star function, okay, and so on, right? So the optimal plan in this sense is quote unquote time consistent. Yeah, as I go further and further into time, I have no reason to change this plan. So here's a proof. So suppose I start with t equals 0. So what do I have? I have that x tilde star is an optimal plan, right? But that means that it attains the supremum given by the value function. This is what I have. And what do I have to show? I have to show this. Yeah. That it satisfies this equality, and this equality is something that I get that tells me that, look, V star satisfies Bellman, and if I put an X star 1 next period in my Bellman, I actually attain the soup of the Bellman. Okay. So how do I introduce the Bellman form right hand side here? So recall from lemma 1 that u of x tilde star must be the sum of f of x naught x star 1 plus beta times the discounted present value u of x star tilde prime starting from tomorrow. So this is from the path x star 1 onwards. Okay, so now notice that x tilde star is an optimal plan, so it attains the soup, and so this must be greater than or equal to u of x tilde for all feasible plans, right? Okay, because all feasible plans must give some discounted present value that is less than or equal to the soup. Okay, so now for any feasible plan x tilde that I have, I can rewrite this u of x tilde, yeah, using lemma 1 again. Okay, so lemma 1 would say, look, u of x tilde is equal to f of x naught x1 plus beta times u of x tilde prime, yeah, for any feasible path, right? So one feasible path is x tilde starts with x naught and then chooses the x star 1 from the optimal plan once, but then follows some other feasible x2 and so forth, right? So for this particular feasible plan, when I break this up, I have u of x tilde is equal to f of x naught x star 1 plus beta blah 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 x tilde prime, where x tilde prime starts with the x star 1 but then traipses off in some feasible direction, x2 x3 etc etc, right? So if I replace this by breaking it up into current and future rewards. And then I consider this inequality. It says the left-hand side is greater than or equal to that. Okay. But since x star tilde prime attains the attains the soup. Sorry. So come back. So that's not the point to start with. It's x star tilde that attains the soup at t equals 1. But consider this inequality. The first term is exactly the same. So if I stay all the way on the x star tilde path, I have this. If I stay on the x star tilde path only for one period, I have this. Right? In the first period, I get the same current return. Yeah, but this is greater than or equal to that. So that means that u of x star tilde prime is greater than or equal to u of x star, sorry, u of x tilde prime for all x tilde prime here, right? So in other words, this is true. But what does this mean? This means that this must be equal to the soup v star of x1. Okay. So v star of x naught is equal to f of x naught comma x star 1 plus beta u of x tilde star prime. I can replace that with the soup. I've missed out a star here. It should be a star. Okay. And now I can use the same argument on v of x star 1, then on v of x star 2, etc., etc. And I get that the along the optimal plan, the Bellman-like equations will attain their soups. Okay. So let's stop here. It seems a reasonable place to stop.